Hello, Dr. Dhiman.
Hi, good evening, all.
Good evening. So we should start our next session. So again, today we have Dr. Dhiman. He is the expert for this session. So yesterday already we have introduced Dr. Dhiman. So I think you can start.
Yes, thank you, Dr. Meena. Uh, Hi, hi, good evening, all. So today we'll discuss various power electronics topology for suitable for EV charger. So before dealing with any converter, we must know what is the effect of high frequency power conversion or high frequency switching. What is the effect on magnetic design, filter design, and all these things. So with the development of new SiC device or GaN device, we can operate the converter at very much high frequency. The switching frequency is not no longer a limitation nowadays. In very old days, we used to operate using transistor and conventional MOSFET, IGBTs and all. There, the frequency of operation is limited to 20 kilohertz, 50 kilohertz. But nowadays, with development of GaN, the switching frequency can go up to 1 megahertz also. So if you go, if you can see this image, this is a 50 hertz transformer, 3 kVA, and this is a 20 kilohertz transformer, the same power rating. So you can see how much the volume is shrinked. Nowadays, everything is high power density. The power density is uh, major parameter for designing any converter nowadays. So everything going to shrink and shrink. So first, I will discuss a brief about phase shifted full bridge converter, or widely known as PSFB. So what happened is that here, uh, so this is an conventional full bridge where the voltage can voltage across this voltage across each bridge can swing from V bus to 0, and from another leg also V bus to 0. Now if you shift one leg, say VCD, shift one leg with a certain angle, then what happened? The common voltage will cancel each other because both are positive. The difference between these two nodes, if you see VAB minus VCD, they are both cancelled, and the difference voltage will appear across the transformer. Now, which is this V primary, this voltage, or V bridge. Now, when a certain bipolar voltage will appear across the transformer uh, current will going to rise. So to control the current, we need the leakage inductance, or this is an external inductance, which limit the rise of current, or you can say the slope of the current. It can control the slope of the current. Now, when you control the slope of the current for this duration, for the small time, automatically your power transfer capability from primary to secondary will also reduce because you are restricting the current flow. So this inductor also act as when output is short circuited, this inductor limit the current inherently. So you can see when this positive voltage appear across the transformer, the to rise. When this is zero, the current going to be discharged, and there is no freewheeling path is required because automatically inductor will discharge. Again, at the negative side, the same negative voltage, when the negative voltage appear across the transformer, this is going to discharge at negative with negative slope at negative direction, and when it's zero, it's going to raise up again. And all the switches are operated at 50% duty cycle with fixed frequency. Okay, now uh, yesterday we see that each MOSFET is not an ideal MOSFET. There is some body capacitance or output capacitance. So that output capacitance, this leakage inductor current can charge the output capacitance. Now, when the output capacitance is going to charge through the leakage inductance during dead time, so the diode going to conduct. Now, when diode going to conduct without giving the pulse, then the voltage across the, sorry, uh, uh, so voltage across the switch, as diode is conducting, so voltage across the switch become zero. Now, when voltage across the switch is zero, now immediately when the voltage across the switch is zero, if you turn the switch immediately at that time, turn on the switch, then the voltage trace across the switch is zero. So when you turn the switching loss or the switching transition become also zero because the voltage across the switch is zero. So this phenomena is called zero voltage or zero voltage switching. This is when you do this, all the ringing effect or the parasitic effect will die out because you are charging the body capacitance parasitics inductance. So your efficiency will, you can eliminate the switching loss, so your efficiency will rise up. And there is no extra capacitance, no extra capacitor, or we are using the parasitic uh, component of the system, and we are achieving more efficiency with that. That is the beauty of this converter. So similarly, when the secondary side voltage will induced, and if you rectify the secondary side voltage and pass through a LC filter, we can have a DC, pure DC value. So there is some control loop. You can sample the voltage and compare with the reference, and similarly you can sample the current and compare with the current reference, and you can implement a CCCV control, which is constant current constant voltage controller. With that, you can limit the current from the primary side, and you can also limit the voltage at the secondary side as well. So this is widely used in battery charging. When up to when battery is initially discharged, you can quickly pump the current using CC mode, and when it reaches to a certain voltage level after charging, then you can operate on CV mode, because at CV mode you can the current limitation is no longer there. You can just push a small amount of current to raise up the voltage. So this is
Sir, why you
widely.
have used a ramp signal? Ramp signal,
uh,
what was the use of that?
so when the output of the controller is a control signal, or it is called the output of error amplifier. So with the error amplifier, you need to compare with the ramp, so that the valid duty cycle or valid phase shift is generated. I will discuss this thing later on. I will show the waveform. So as you can see, if you change the angle phi here, then this opening of this pulse will go on, right, on the top side and in the bottom side as well. So this, when it go on, you can see with change in angle phi, you can control the duty of the transformer, voltage across the transformer, without changing the duty of any switch. If you have any question, you may ask, please. Okay. So now whole this primary side, we can see like this is a pulsating voltage here. So we can model this thing as a pulsating voltage, and this is the output inductor, output capacitor, and load. So all your converter is now become uh, just a square wave with double switching frequency, because this is a diode rectification. When you rectify any signal, it become double frequency. So this is similar to a buck converter. When you simplify the whole converter, it looks like a buck converter. Here, this is a pulsating voltage having a fixed duty, and this duty is the phase shift angle is converted into duty, and this is the normal filter, LC filter, and this is the load. So you can do, if you analyze the voltage, analyze this output to duty transfer function, the current injection to in function of duty, then you can get the control to output transfer function, and you can do the Bode plot to design the control of the this voltage CV controller. Now, if you when CC mode is there, or CC controller, current controller, so now if you you can model this voltage source with series inductor as a current source. So this injection of current is actually cause the raise of voltage across the output, because this current is pumping to the output capacitor. Sorry. So this is the control to output function for the voltage loop. This is the control to output function for the current loop, because when you increase the duty or increase the phase angle, the current injection will go up. So now this is phase and magnitude plot of both two loop. If you do the transfer function, you can see this kind of Bode diagram. So from there you can have the crossover voltage, crossover frequency of voltage loop, crossover frequency of current loop, and from there you can design the controller, any kind of controller, type 2, type 1, type 3, how much gain bandwidth is required, how much phase margin is required, you can calculate. If you want any detail about this, you can refer to my paper in IT system integration. Now came to dual active bridge converter. So earlier the same converter. Now if I replace the secondary side with active bridge, earlier there is diode. Now we replace the converter with another active bridge. So now this is active high voltage side bridge, and this is voltage side bridge. And earlier there is one load. Now we disconnect the load and connect a voltage source like battery, and you may say at high voltage source as a grid. it's a DC voltage from the grid. So this is galvanically isolated power transfer scheme. This is very much popular nowadays, and solid state transformer and all these things use this kind of topology. So this is when there is two voltage source, and these two voltage source interacting with each other, they can exchange the power between them. This DAB, dual active bridge, is widely used. So the efficiency of dual active bridge is very much high, because there this leakage inductor, this external inductor or leakage inductor is also participate in zero voltage switching. It can charge this body capacitance, here also body capacitance, and the secondary side also, because this inductor will also reflect to the secondary side by a factor of n square, because this is a transformer this is just a transformer which can translate the everything from primary to secondary with a factor. So similarly, at the secondary side, you can also achieve GVS. So in this converter, every switches can be operated at zero voltage switching, or that is called soft switching. Now, another beauty of this converter is that you can operate the converter in very wide range, and this inductor is also restricting the power flow. So if anything happen, any short circuit happen in the secondary side or HV side or LV side, this inductor will limit the current. It will not allow for huge current. These are inherent protection of the converter. Okay, so now this is the operation mode of operation. There is 4 mode of operation. So when these 2 diagonal switches are on, so this voltage will appear, because this is a full bridge. So bipolar voltage will appear across the high voltage side. Similarly, a bipolar voltage will appear at the low voltage side. So when you slowly shift the angle between them, this transformer will see there is a voltage difference between these 2 winding, and this difference in voltage will appear across this inductor. So inductor current is going to be rise. Now here you similar concept of PSFB. This common voltage will cancel each other. This is at mode 2. So you see this mode 2, this common voltage will cancel each other. So because of this common voltage, there is no voltage difference. So the inductor will try to discharge slowly. Okay, so if you observe any converter, any flyback converter, any kind of converter, any full bridge converter, you can see the current rise immediately, and here it touches the zero, it fall immediately. So DIDT phenomena is very high, because with a short period of time, which is dt is very small, a huge amount of current is flowing in the all the trace and all the wire. So that initiate the that initiate the that radiate the signal, and all your traces and all these things, all the parasitics act as an antenna, because this DIDT is very high. So a huge amount of flux will radiate from your converter, and when this flux will radiate, it is called radiated EMI. This radiated flux can interact with uh, any kind of conductor nearby, just like and produce the eddy current, and that eddy current create the noise, and your controller can be malfunctioned. If you're using any monitor or anything, all this thing can be malfunctioned because of this high DIDT. It's act like an induction oven. In induction oven, a flux is generated, and this flux is circulating inside your pan to generate the heat. But in this case, in any power converter, this kind of phenomena is always generated. So we need to take care that DVDT, rate of change of flux, should be controlled, and also DIDT and DVDT both should be controlled in controlled manner. There is no abrupt DVDT or any DIDT. So when naturally in this converter, as this voltage is similar, so it die down slowly, and in the negative direction also, it goes to the negative, and it again, this at mode 3 and mode 4, this phenomena going to be happen cycle by cycle. Okay, so this is one simple DAV controller where I need to, okay, so another thing is that the power is flowing from leading bridge to lagging bridge. You see here, the leading bridge is high voltage bridge. So from high voltage to low voltage side, the power will flow. If you reverse the direction of this phi, the opposite, from low voltage to high voltage, the power can flow. That means you are charging the battery, you can discharge the battery as well without interchanging anything, just with control. So as it is a bidirectional converter, so there should be a directional input of the converter. Now this is the directional input, and this is the enable. Means if anything goes wrong, you should shut down the converter. So that is enable switch or enable. These are control signal. If you make it on, the power will flow, and if you make it off, the power will stop. The power flowing will going to stop. And the direction is when you reverse the switching sequence. That means if you make the Q1 to S1 and S1 to Q1, sorry, S1 to Q1 and Q1 to S1, that means you are making the lagging bridge to leading bridge to lagging. Just an simple example of mirror. So if you see from the mirror side, you can see something is lagging, and if you see from the opposite of the mirror, you can see that the same thing is a leading because of the reflection. So similar thing can be implemented using switching marks or switching multiplexer. So here your since it is used for power controller, so you need to multiply voltage into current and convert it into power. And since it is a bidirectional converter, so this power can be both plus and minus, because when any power going to the entering to any system or entering to battery, you can consider as negative power, and when the current is outward to the towards from the source, you can assume at positive power. This is just a sign convention. You can assume anything. There is no hard and fast rule. And so the PM is plus and minus, means having bipolar. But your error amplifier or your PI controller is cannot process the negative value, right? Because you are tuning the your PI controller to positive. Your reference is just a positive integer, so, or positive voltage. So it cannot take the negative voltage or negative integer, because when it sees the negative voltage, it can assume it is 0. now to do that, we need an absolute value amplifier, so that only the value will go to the PI controller instead of the polarity. This is just like an, you can say, the rectification. But if you do the rectification, the normal diode bridge rectification, the voltage will drop across the diode, and this is very low level signal, around in the range of 2 volt or 3 volt maximum. So if you drop 1 volt across the diode, you cannot allow that drop. So your controller will see some offset. So to avoid that, we need to implement a absolute value amplifier, which is an active rectification. Now, this using active rectification, the mod value of power measurement is going to is compared with the power reference and produce and pass through a compensator and produce a control voltage. Now, this control voltage is going to phase modulator and produce the gate pulses. Okay, now when you're going to do elective bridge, you can assume you can just replace the whole bridge with a switching function. This is first harmonic approximation. This is widely used when you analyze any converter. So your complete S S1 to S4 is completely become S of t, where S of t is plus minus 1, as it is full bridge. If it is hard bridge, this is plus 1 and 0. Now, if you multiply this plus minus 1 with this voltage or input VBus, so you can see a jump. You can see the same switching phenomena as a switching function mathematically, that plus V and minus V. So your complete system will now small. Now you can see the equivalent circuit of dual active bridge is going to adjust your switching function from the primary side, and one inductor and one transformer, which is just an translation, and similar switching function at the secondary side, and this output the voltage capacitor and the load. Now okay, now you can, if you do the averaging model, okay, so now if you average this switching function only, you can see, if you make it first order approximation, first harmonic approximation, or any kind of linearizing tool, if you make the S of t or Q of t just a function, then you can see everything is linear element. Rest of the thing are linear element. There is no longer any nonlinear function or nonlinear element. So now if you do the dynamic equation at HV side and LV side, you can, if you do the KCL, KVL, those things, you can end up with this equation. So finally, my goal is to inject the current from primary to secondary, or high voltage to low voltage, or low voltage to high voltage. And with respect to the control parameter is phase shift or the duty. So now this is the, if you make it with state matrix, and so this will be the state voltage and to the inductor. You can see the real value, imaginary value, and some DC value also. So for this unit, now you can end up with state matrix, A matrix, and the output matrix, similar like x dot equal to ax plus b. I think all of you are very much expert in this theory and all this thing. So now if you do the Bode plot, it is look like this, and this is the magnitude and this is the phase, Now similar thing, if I want to verify whether my transfer function is right or no, so I can I can break this loop and inject this control, break this loop and inject a small control signal with different frequency. So, and we can observe how the effect of this perturbation is appear uh, at the current flowing from HV to LV. So if I do that at different frequency, I can see a dot is coming because this is a discrete thing. So now if I match with the analytical approach, means analytical this transfer function, I can see my transfer function is right and it match almost every point. So now this is an uncompensated system. If I want to design a controller of that, so I need any kind of type 2, type 1, any kind of thing. So generally type 2 compensator or is used widely uh, because it has a pole here, pole at origin, this C1. This will give a DC boost since a DC to DC converter, so DC gain should be high. Now if you see the overall system, you can see this is the Bode plot of the compensated system. Now with that we can gain the gain margin we can tune to this dB. It is completely dependent on the parameter you are using. If you choose a different system, different component, this will make different, and I can gain a phase margin. I can allow the phase margin to 90 degree. This is very much widely used tuning. If you do any kind of tool like smart control, in MATLAB also there is some CISO tool, right? See, system input, system output tool. With those tool, you can check if you give the transfer function, you can see how much gain margin and phase margin you can allow in the system. From the gain margin and phase margin, you can design all these components. This is the actual experimental setup of this kind of thing. If you need any detail, if you want to read any detail, you can refer to this paper where every design equation and everything is there. How to tune every parameter, how to design the control loop, how to design the compensator and all that. So this is this picture I shown yesterday also. This is 1200 volt SIC device, and I made a system of from 380 volt to 48 volt, which is standard voltage level for microgrid. So I can transfer from power from 380 to 48 and vice versa also. This thing I showed yesterday also, this gate driver. This is that dots incorporate all the transfer, all the advanced function, protection function. Okay, now see, this is the voltage ramp. I think Mr. Jadhav is asking about that. So when, if you see, it is you can assume this low amplitude to be 0 and this to be 1. So now if you swing a control voltage in between this ramp, you can see the when this green signal cut this voltage ramp, it can generate a phase shift of phi. You can see at dot by dot point. If you increase the control voltage, that means if you increase the amplitude of green line, you can see this. If it is there, then the corresponding phase shift is this. So this is a voltage to phase converter, or you can say phase modulator, where if you inject some voltage, it can modulate the phase. Now when phase is modulated, Now when phase is modulated, your amount of injection of current is also going to be modulated. Now if I see, this is the constant, this V control is a constant value. Now if I use, instead of constant value, some small 1 kilohertz signal, then this green value will dance at 1 kilohertz or oscillate at 1 kilohertz. So similarly, this phi will also oscillate at 1 kilohertz. Now when phi is oscillating, so my current, output current will also oscillate with phi. So indirectly, if you, this is my control signal, and if you measure the output current, so you can make a relation how output current is affecting with changing in control signal. And this is very much very common practice when you model any converter in live desk. You want to verify whether your mathematical derivation is right or wrong. This is widely used method, and there is no alternative of this method. This is very perfect method. So from there you can see your transfer function is right or no. From there you can make experimental validation of your transfer function. You can model any kind of converter. If you don't know the transfer function, you can, from this relation, you can build a transfer function, or you can just simply simplify the transfer function. It makes your life very simple.
Sir, what should be the value of the ramp signal magnitude?
It depends upon your IC. Generally, for mathematical derivation, we assume from 0 to 1. But here it is not 0 to 1. I think it is 3.3. See, this is 500 millivolt. Yes, I think it is 3. 1, 2, 3. Yes,
So
2
how
volt.
do we
Around 2
decide
volt.
this ramp signal value, sir?
How?
We will decide that we are taking one value at that time, what 3.5. How we are going to decide this ramp signal, magnitude of the ramp signal?
Okay. So there is different. Okay. When you charge a capacitor with a constant current, what will be the voltage profile of the capacitor? Hello. Hello.
Yes, sir, please.
If you charge a small capacitor with a, say, 1 milliampere, what will be the voltage profile of the capacitor? How the capacitor voltage will look like? Okay. So when you charge any capacitor with a current source, constant current source, the voltage will just integration of the current injected to the capacitor, right?
Yes.
Yes. Now when you integrate a constant value, what you will get? C. If you integrate any C, what you will get?
Constant,
C
it
into,
will be constant step signal it will give.
no. When you integrate a
Uh,
DC,
yeah,
if you
we
have a
will
DC
integrate
signal,
this,
if
then I
you
will get
integrate
the
it,
ramp signal. It will
ramp
be
signal,
ramp
right?
signal.
Yes.
Yes.
So this ramp signal you can get there. Now there is a limit that you have to decide how. So the ramp signal is go on increasing. Now you need to decide when you discharge the capacitor, at what value you need to discharge the capacitor. So if it is starting from 0 and going to, say, this is 2.5 volt, Now you discharge the capacitor. Now say if you allow to rise up to this and you discharge here, so your switching frequency will change.
Yes.
So this completely depend on what is your switching frequency. If you tune the switching frequency, you can discharge this, you can adjust this discharge cycle. Also you can adjust the injection of current. Generally it is done by a resistance, series resistance to through your voltage source. If you take any kind of modulator, any kind of PWM modulator, you can setting RT and CT. CT is for this timing control, and RT is just this resistance, or the timing control. If you see this paper, there everything is detailed discuss how ramp is generated and all these things, which IC is used to generate this ramp and all these things. So if you see when the ramp is the ramp signal is cut, when this control voltage and ramp signal is matched together, this is just a simple PWM block. So I am using this PWM block with generating the phase instead of duty. In control of buck converter, you are using the same philosophy, right? You are comparing the ramp with the control signal, and you generate a duty, right? So that duty cycle I am converting into phase. So now you see when I generate the phase, the current will shoot up due to that during that phase. Now if I allow the phase more, the raise of this current slope is go more, so the average value of current will be more. So the DC current, injection of DC current will be more to the system. Now if you see, if I oscillate this signal, you see this phi will oscillate and this current peak will also oscillate. It will vibrate like here with a small value. This is called the perturbation. In mathematics, we do the small signal perturbation when uh, we break the component x into x plus small x bar or tilde. The similar thing is done in the hardware. See, if this is a bidirectional power flow. See, this low voltage bridge is lagging from the high voltage here, and here you see the low voltage bridge is leading compared to this high voltage one. So see, the current is flowing, the current profile is same, but when I just change the direction input with the switching multiplexer, we can flip the signal and we get a leading or lagging voltage. Okay, so now this is the zero level. When I change the direction, you see from minus 6 amps to 6 amps, it is transferring current. And when I make directional input again 1 to 0, so opposite side current is flowing. Do you have any question up to this? If anybody have any question, most welcome.
So simulation can be possible for this.
Yes, there are a lot of simulation tools nowadays, PCM and all these things. I will show one simulation of LLC converter. I don't have simulation for this DAV converter because this is my PhD work. So, long time. So I don't have simulation right now, but you can simulate in MATLAB also. And all this transfer function, derivation of this transfer function, you can do at MATLAB, and you can verify with the experiment whether your computation is right or wrong. All this is MATLAB figure. this Bode plot and all these things. Or also you can insert the experimental data with MATLAB also. That is very much flexible nowadays. Any other question? Did I answer your question? Okay. So now this is another very much popular topology, which is called LLC resonant converter. See, this is an resonant element L, and this is a resonant element C, and this is the magnetization inductance of the transformer. So here you can see this is L, L, and C. That is why this topology called LLC topology. And here the resonating element is just L and C. Two 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 component resonant. You can make a different combination of LC, but this is the most popular, and this is series connected. So this is called series resonance topology or series resonance. Okay, so there is different combination of LC. With that LC you can make any kind of filter and all this thing, and you can implement it here. This is I also encourage all of you to make this LLC converter and study the LLC converter. This is very simple to implement at lab. This is very simple converter to implement. So this side, secondary side, you can either rectify with diode, or you can replace the diode with MOSFET for synchronous rectification. And this is the synchronous rectification is used at high current application. This is very much used in telecom power supply. I am designing telecom power supply in my company, so I am very much familiar with this topology. This is very nice topology, and here all the parasitic element is just, since this LC is a highly tuned filter, so your all the parasitic noise just automatically go down. It's automatically attenuate. And here you can see this. You have the output capacitor. So this resonant current, or this current, is interact with this capacitor and also produce the 0 voltage switch. At the secondary side, this is a kind of sine wave. So if you rectify a sine wave, it switch at 0 current, right? Your commutation happen at the diode is at 0 current. So it's naturally 0 current switching happen at the secondary side. No need to do any external mechanism to make the current to 0. But the problem is if you see the gain curve of this LC network, this is very much load dependent. This load, if you transfer this load, reflect the load to primary side, you can see this load is acting as a quality factor of your tank. So this is very difficult to control. The regulation is very difficult, and you cannot have a very wide gain like compared to other converter. And see, here is this is just a the control parameter. If you sweep the frequency, you increase the frequency, the attenuation will happen. If you decrease the frequency, you can gain some voltage. Okay, so what is the resonant and natural oscillation? See, if you see if you take an example of a pendulum, if you trigger, this is the natural position or rest position. Now, if you trigger one pendulum, it will just oscillate like this, back and forth, and the natural frequency of oscillation is 1 by 2 pi root L by G, right? So that is called natural frequency of oscillation. You just triggered the system and it naturally oscillate. Now, due to air friction and all these things, due to the non-linearity in air friction and practical scenario, slowly this oscillation will die down and came again to rest position, right? If you take any kind of system, say spring mass system or any kind of LC system also, if you triggered one LC, you will get 1 by 2 pi root LC, those natural oscillation. But after certain time, the oscillation going to decay because of the resistive element in the system. The power of the oscillation will damp into the resistance, will absorb by the resistance. Now, if you give a force oscillation along with the natural oscillation, suppose we, in this case, we assume that this point is fixed. Now, instead of this fixed point, if you also vibrate if you make a oscillation of this point, if you vibrate this point at the sync with the natural frequency, then what will happen? So this oscillation will sync with the natural oscillation. So when it try to die down, you are not allow the oscillation to be die down. You again push some energy so that it gain the energy at next cycle, which is second cycle. At first cycle, it is natural oscillation. At the second cycle also, it can retain the same energy. At the second cycle, the energy should not be lost. So that thing you can by pushing an external energy. Similar concept, if you apply to power converter, that similar concept that this pushing of energy is done by a switching network or half bridge or full bridge. So now if you do so, you can make the frequency similar to the natural frequency of the converter, that is natural frequency of the tank, LC tank, which is 1 by 2 pi root LC. Then what will happen when when it triggered, the first peak will appear like this and second peak is like this. So again, you are, instead of when it's going to die down, you are again pushing some energy from source. This is voltage source. So again, it gain the energy. Now, if you model this converter, it is like this. This is series element LR and CR, and this parallel is the magnetizing inductance of the transformer. And if you transfer the load from secondary to primary, there will be some factor of n square, and this reflected load is loaded here. So the tank current is composition of resonant current and magnetizing current. So this magnetizing current is fed back to the switching network. So this magnetizing current is responsible to charge the output of the capacitor. Now, there are a lot of equation and very complex mathematics is there. How much will be your LM? What is the relation between LM to LR? Because this LM is reactive current. You are feeding back the current to the bridge. You are not transferring this current to the load. At load, only tank current will transfer. So there are a lot of mathematics and all these things, and still there is no clear answer that how much should your LM and how much should your LR. All depend on your design. How you design, which switch you are choosing, what is the output capacitor of the switch, how much from what power you want zero voltage switching, all these things. So this reactive energy I am taking from the source instead of transferring to the load and feeding back to the source. This is a quite difficult mechanism for other converter, but in LLC this thing happened automatically. This is the beauty of this converter. Now if you see, if you do the transfer function and Bode and all these things, you can have this. This is the gain curve of the tank. So when it cross the peak of this thing, this is called capacitive region, this is called inductive region. So if cross the capacitive region, this is called zero current switching region. I will show some simulation and some experimental waveform also. And when you go for buck region, automatically GVS. You see, and this is one simulation result. This is the simulation result of half bridge. So this bridge voltage is 0 to 1 only, or 0 to V bus only. Here I have taken 100 volts, so 0 to 100 volt. You see and this is the current flowing through the tank. See, this current is composition of sine wave and square wave, a triangular wave. The triangular wave is just from the magnetizing current, and this triangular wave is reflected at the switch current. You see, this is the switch current, and you see a sharp current is flowing here. Now this sharp current is negative in nature. Now negative current means some current is injecting to the device, right? This is the conventional sign of the current. So this negative current means this is charging the capacitor. When the capacitor is charged, your body diode will start to conduct. Now when your body diode start to conduct, you need to turn on the switch. That is called zero voltage switching or zero voltage transition. So in converter, it happens naturally. And in one cycle of the tank, current is flowing to the switch. Now this is the exact actual practical waveform of the LLC converter. You can see this is the tank current, the green one, and this is the bridge voltage. You can observe that the bridge voltage is not abruptly going from low to high. See, it is following some slope. It following some curve. Since the output capacitor of MOSFET is non-linear in nature, this is the output capacitor of the MOSFET is not linear capacitor. It depends on the voltage. So as the voltage rise, the capacitance is going to change. So that is why you can observe there is this slope is different, this slope is different, and it following some slope instead of just going shoot up to certain value from 0 to 1. And you can see the segment of the turn on is from here to here, and during that, at the secondary side, the resonating current is following from half cycle. This is the zero axis, you can see, but the tank current is not following positive half cycle symmetricity, sync with the switching sequence. So why it is so? If you zoom this section, you can see when voltage is rising from 0 to 1 or 0 to V bus, there is still some negative current flowing from flowing to the tank, and this negative current is transferred to the switch. You see the amplitude, this the this negative current reach the zero here. You see, so from here to here, it is charging the output of the capacitor. Negative current means the current is going towards the switch. This is the natural phenomena of the converter. You no need any extra arrangement, extra commutation, extra anything. We are just using the parasitics of the circuit to achieve the GVS. Okay, now and this yellow one is the voltage across the resonating capacitor. You can see there is 90-degree phase shift between current and the voltage, since the capacitor voltage and capacitor current are 90-degree phase shifted. You can observe all these kind of phenomena in this converter. So this is no load condition. You can see this secondary resonating current is 0, but your magnetizing current is linear, because you are charging the inductor linearly, and your tank is no longer acting. It is just LM which is acting. You can see there is no load, but you see the voltage waveform of the switching node is still having GVS. You can see there is no sharp shoot up. This is rising slowly and also dying down slowly. This is very much this is very much interesting phenomena, and it gives low EMI at the circuit. You can take any power at the resonance, any amount of power, theoretically infinite amount of power, and but your EMI, EMC, all this thing will not affect at all, because it is operating at resonance. That is why every telecom equipment, every telecom converter try to use this topology. This is very well used topology. Okay. Now you see, when I reduce the amount of magnetizing current, this slope. So see, this is only GVS. This region is very small, but it rises up sharply. So this region is called hard switching region. Yesterday I'm showing some plateau, threshold. So this thing just crossing those region, and here this is the region where switching loss happen. Now if I make magnetizing current further, reduce the magnetizing current further, you see this is the ringing you can observe across the switching node. This ringing you can see in the lab when you're doing anything without zero voltage switch. You can observe this kind of ringing, and if the voltage is high and power current is high, the amplitude of this ringing destroy your MOSFET. Okay, so I make a simulation simulation here. So you can see this is the tank current, and this is the voltage across the tank, and this is the output voltage. This is half bridge topology, or you can say this is the only half. This tank is faded by half bridge only. Now, and this is the switch current. Okay, you see. Okay, now if I increase the frequency, you see this is the negative current. Small amount of negative current is flowing through the switch. That means it the tip of the resonant and going to the inductive region. Now if I make it further, you see there is huge amount of reactive current flowing through the switch, but your zero voltage switching is very prominent. Now you have to design how much current you want to allow. This current is controlled by magnetizing LM. Here I put LM. Okay. Now you can see this is the current waveform. You see current waveform of the tank. You can see the cycle is not yet completed. It start here along with magnetizing current. It not completed yet, but again you are pushing the opposite side of the oscillation. So that is why it is on buck mode, or you can say inductive mode. Now if I reduce the frequency, you can see when I reduce the frequency, this negative current is shifted from here to here. That means here it happens GCS and it goes into capacitive region of the gain curve. So here it this is GC negative current at turn off, but I need negative current at turn on. So when you operate at this condition, your switch will definitely blow, because this zero current cannot do anything with the voltage, because your switch is very sensitive to voltage. But if you see the tank current, you see this is my switching window. With this window, it die down before closing the window. That means it is high frequency. That means it is a capacitive mode. Now at inductive, at resonant point, yes, at resonant point, see, this is exactly following the envelope, and your switching current is also this current is flowing through the switch, and this, see, there is no negative current also. So at resonant mode, so generally we try to operate the converter slightly above the resonant mode, that is inductive mode, because of this zero voltage switching. If you have any question, you may ask, please. That's all from my side.
Hello.
Yes.
Dear participant, if you have any question, you can ask in the form of, you can ask directly, or you can write in your chat box also. Hello. Participant, please. So we'll share this recording also. Okay. And as well as this experts contact details like email ID, so that in future you can contact with this concerned expert. And from the organizer side, Dr. Dhiman, thank you. Thank you for
Yes,
the
thank you.
delivering of your lecture. Right. So in future, we are again planning for some other courses. Okay. So thank you. Good night.
Yes.
Today
Yes,
we'll
good night.
concluding. Tomorrow
Good
again
night.
we'll meet sharply at 6. Thank you.
Thank you very much.